just begin the presentation then.
Great.
Thank you for the introduction. I am Angela Middleton, Senior Archaeological Conservator with Historic England, and I will start this presentation by giving you a bit of an overview of the history of the ship and some project background. I will then pass on to Sarah Paynter, a senior material scientist, who will talk about her work on the glass beads. And we will finish the presentation with Francesca Garadi, also a material scientist, who will focus on her work on the silver coins. The Rooswijk was built in 1737 for the Chamber of Amsterdam of the Dutch East India Company, which we also refer to by the abbreviation of VOC. The Rooswijk completed one return journey to Batavia, which is in modern-day Jakarta, during 1738 and 1739. It then prepared for its second outbound voyage early in 1740, but only one day after leaving the Netherlands, it got caught in a severe storm and sank in English waters on the Goodwin Sands. And you have marked the location of the wreck here, approximately in this cluster of wrecks. The wreck and artifacts are owned by the Dutch government, but they're managed by Historic England. The Rooswijk was a trade vessel, and the only cargo that was recorded by the Dutch East India Company were the silver coins and the silver bullion, but it had loads of other trade goods on board, and we're going to hear a bit about that today. The wreck was rediscovered by sports divers in the early 2000s. The Dutch Heritage Agency, which we refer to as RCE, assumed ownership of VOC ships abroad. The Rooswijk has been protected under the Protection of Wrecks Act since 2007, and Historic England is managing this protected wreck on behalf of the Department for Digital Culture, Media and Sport. So you can see how this wreck forms part of our shared cultural heritage and responsibility, and it's only fitting that both heritage agencies work together in this project. The wreck was classed as high risk on the Heritage at Risk Register due to its exposed remains and vulnerability. The project began with a geophysical survey in 2016, which provided further evidence for the at-risk status. A multi-beam survey revealed changing sand levels, showing that the Rooswijk was increasingly being exposed. The Goodwin Sands, where the wreck is lying today, are extremely mobile, which means that the wreck is periodically uncovered and then covered up by sand again. Another risk to the site comes from illegal diving. So it is well known in the diving community that there is silver on board of this wreck, which makes it extremely attractive to illicit activities. So in response to these threats, the Rooswijk 1740 project was developed. The aim was for an international team to excavate, record and assess an area of at-risk remains of the Rooswijk, contributing to an enhanced understanding of the wreck and establishing a way forward for the future management of the remains. What followed was a huge excavation project over 2 field seasons. Almost 400 surface supply dives took place, and the diving support vessel was moored on a 4-point mooring system near to the wreck site, and excavation took place using surface-powered airlifts. The divers were tracked, and the position and data information of artifacts was recorded using site recorder software. After each excavation season, the artifacts were then transferred to Portsmouth on the south coast of England, where the Historic England Conservation and Research facilities are located. And here we work on the artifacts with a multidisciplinary team, and I will give you a brief overview of the conservation work that has happened to date. An underwater excavation on a wreck can very quickly result in a huge material archive, and the Rooswijk was no different. During the excavation, the team allocated almost 2,000 find tags, but the actual artifact count is much higher. And as I proceed with my part of the presentation, we'll look at a few examples. This is one of the many chests with content. This one contains symbols that were used for sewing. On recovery, this chest was given one artifact number. But when we zoom in, you really understand how tightly packed and full this one chest is. And it's just full of symbols. So the actual artifact number that we are dealing with is much higher than the 2,000 artifact labels that were allocated during the excavation. One of the first things we did after the artifacts arrived at our research facilities was to X-ray the many concretions and other mainly metal artifacts. The X-rays create an essential record of the condition of the artifact, but they are also instrumental in identifying and quantifying objects. As soon as artifacts were recovered, they were placed in fresh water. This preserves them and stops uncontrolled drying out, but it also starts the very lengthy process of desalination. Once back in the lab, we carry on with desalination, but we are now using distilled water where we can. We also have to make artifacts available to other researchers and coordinate their access requirements around various treatment schedules. In conservation, we use a variety of tools to remove concretion and corrosion layers to micro-excavate objects. This will help speed up the desalination process and at the same time reveal surface features such as tool marks, maker's marks, or decoration. Now let's look at one concretion in more detail to illustrate how we work. A concretion forms around a corroding iron object. Iron is very unstable and its corrosion products are much larger in volume than the original artifact. And often corrosion continues until there's nothing left of the actual artifact, and we can see that in the X-ray images as dark voids in the shape of the artifact. So those are the dark voids here that were left behind by mainly nails in this case. But when a concretion forms, a whole load of other materials, such as surrounding seabed sediment, stones, shells, and other artifacts, also get incorporated into this concretion. And they form a really hard mass, sort of a big lump, and that's where the name concretion comes from. Now, how do we work on these? Well, first of all, we use the X-rays to guide us. And our favorite tool is probably the air scribe. This is a pneumatic tool where the tip vibrates and removes the overlying concretion. This can be very messy and noisy, but it can achieve very good results at the same time. And here is the same concretion again that we looked at just earlier. You can now see the nail voids, which have been exposed, and they are empty. There's nothing left of the actual artifact. The images at the top show some of the glass and copper alloy beads and rings micro-excavated from the concretion, and the yellow and white specks that you can see dotted all over this concretion lump are yet more glass beads that need to be removed. This work is really quite tricky, and often we swap over to another tool, the ultrasonic scaler, because it allows us to work on a much smaller scale. Artifacts or ecofacts, such as animal bones or plant remains removed from these concretions, then get passed on to the relevant specialist, and they then enter the conservation treatment cycle. Large concreted artifacts follow the same principle, only in these cases, the logistics of moving such heavy and large objects have to be carefully considered. Here we see one of 3 casks with content. All casks recovered from the Rooswijk contain iron nails. This one, however, is the only one that has an owner's mark or a maker's mark inscribed on the headpiece, and I've enlarged that here. So it's on this headpiece here, and you can see a more detailed photograph there. Such personal connections to the Rooswijk offer an incredible insight into East India trade operations of the 18th century. Sorry, just a second. As has already been shown, marine concretions can play a crucial part in preserving materials and artifacts that normally don't survive very well in the marine environment, like textiles, for example. Made from natural materials and sort of a large sheet, but often lightweight, they easily break up and float away underwater after the ship sank. However, textiles would have been used in abundance on ships, but because of their lightweight nature, we don't tend to find them a lot from wreck sites. So uses would have included obviously sails and clothing, but also for storage containers such as sacks and bags. And here we have 2 examples where textiles have been preserved during the formation of the concretion. On the left, we have a pair of pistols. And when the concretion was removed from the pistols, large sections of mineralized textile were uncovered. On the right, we have the remains of another chest. In this case, this chest contains saber blades, and you can just see the tangs, the iron blades sticking out here and still surrounded by concretion. On the outside of this chest, so on top of the wood, mineralized remains of textile were noticed. And we're referring to this as mineralized as the textile is heavily impregnated with mainly iron corrosion products. So here are 2 detailed photos of what those textile remains on the outside of the chest look like. As textiles are a rare survival from underwater sites, it was important to fully record and analyze the remains. In the first instance, we produced dynolite images as well as transmitted light microscope images. And we then worked with Francesca to obtain SEM images. Our textile specialist is based in a different country, so we worked with her remotely, and she undertook the fiber identification and description of the textile fragments. In the case of the pistols, the fiber were identified as wool, which was used to produce a felted fabric, which was then wrapped around the pistols. And the textile fragment from the chest was identified as bast fibers. This is a common fiber used, especially if you think about all the robes used on a ship. They are also mainly made from bast fibers, normally hemp. In some cases, though, separating objects, like I've described the process on the concretions, may not be the preferred option. The Rooswijk was a trade ship and had a known cargo of silver on board. A lot of coins were found in stacks, such as this one here. And to us, this is a powerful relic to tell the story of how silver was packed and transported from the Netherlands to Batavia. And although we have separated most coins, in some instances, we have decided to leave coins fused together in those stacks to illustrate the silver trade. But how do we then collaborate with the numismatist in this case? And how can we get the information of each single coin to them, which is a request that was made by the numismatist? Here we undertake micro CT scanning at the University of Southampton. This is a powerful and non-destructive method to virtually separate and slice the coin stacks. You can see the clarity or the resolution that you can achieve with micro CT scanning, and how these images can then be used by the numismatist to undertake dating and provenancing of the coins. Before I finish, I wanted to share one last example with you. Sometimes we make discoveries in unexpected places. The concretion shown here mainly contained iron shot, but amongst the iron shot, we found the neck of a glass bottle, which you can see here in the middle. During cleaning of this glass bottle fragment, a white residue became visible around the glass neck opening and on top of the cork, which you can see here in those images at the bottom. Francesca undertook the analysis and established that this residue is colophony, a waterproofing agent applied to the outside of the bottle and the cork to provide a seal and make the bottle watertight. And as we continue with the conservation and analysis of the different objects, we will reveal maker's marks or decoration, such as on this pewter jug or the trumpet. We will continue work on the chest to find out about their content. We will be able to quantify the recoveries, which will give us a better understanding of the scale of trade that was going on in the 18th century between the VOC and the East Indies. We will continue with material analysis to research the composition of the various materials and might even be able to say where certain raw materials came from. So although diving has stopped, discoveries are still being made. And this is a good time where I hand over to Sarah, who will tell you about the sort of discoveries that she is making.
Hello. Hopefully everybody can see and hear me okay. Yeah, excellent. Yeah. Right, I'll just try and get the presentation going. There we go. Is that all right? Everybody can see okay?
Yes. Yeah.
Lovely. Thanks, Angela. So
yes, we can.
Oh, great. Thank you, Rocco. Just like to thank the organisers for including us today. It's been really interesting. I've learnt a lot. So my name is Sarah. I'm a material scientist with Historic England. I work at Fort Cumberland Laboratory in Portsmouth. We do a little work on collections and slightly more work on heritage buildings, but most of the work that we do is on material from archaeological sites or from wreck sites. And our involvement comes before it reaches the museum. So we're in the post-excavation stage, and Angela's shown you the condition that a lot of the material comes in. Our remit is mainly England, although not always, as here. So occasionally we get to work on material further afield. We're very fortunate at the fort because the team there is multidisciplinary. So we also have pollen specialists, we have geophysicists, we have dating specialists, specialists in human and animal bones. So those people are within the same building and we can go and consult, which is a lovely way to work. Now I'm going to talk about the glass from Rooswijk. There was a lot, many bottles, gin and wine bottles, some of which Angela showed you. We also had some nice drinking vessels, Bohemian crystal, some window glass, which you can see in the middle there, and one very nice chevron bead. But I'm not going to be talking about any of those. I'm going to be talking about the very plain glass beads that were found in the concretions. Now, I think that you are all very aware with the techniques that we use. We have XRF, portable XRF, SEM, EDS, XRD, and FTIR. So I'm not going to go into the techniques today. I'm going to mainly focus on why we analyze things and how important people like you are to archaeology, what we can contribute. Some very brief background on bead making before I start. So this is us on the left doing some experimental archaeology. We're making beads by winding, where you have a melted cane of glass which is wrapped around a mandrel. The beads from Rooswijk are largely drawn glass beads. So in that case, you draw a cane with a perforation, and then those are cut into even lengths. You collect it in a bundle. The glass worker would sort of hold the end of that bundle over a chisel set in a bench, and then they have a blade and they manually cut these tiny beads. They're about 4 millimeters diameter. And then they're sort of fire polished by heating and tumbling. And if you have time, this YouTube link is to Glassworks in India, which is no longer operating, unfortunately, where they're making the beads using these methods, and it's fascinating. And I believe that UNESCO have recognised this type of bead making as an intangible cultural heritage now for Italy and France. So I use scanning electron microscopy. The reason I did that is partly it's in-house, so it's convenient, and partly because if you look at the backscattered image of one of the beads on the right, and then there's a close-up which shows the weathering layers on the bead, and they're also covered in this iron mineral scale from the concretions that they've been extracted from. So if I use a surface analysis technique, I'm going to get altered glass and the things that are stuck to the surface. If I use SEM, then I can select unweathered glass, and I can also visualize the colorants, the opacifiers that are in the glass matrix, and those are quite important. The lab itself has been going since 1950. So we have an awful lot of reference materials to refer to. And one of the things that's very important with our work is that we have many standards for metals and glasses with compositions matching archaeological and historic materials. So modern materials are very different. They're not really as useful, but we have this big data set of standard materials that we can check against, and then we make sure that our data is comparable to the data produced by other laboratories. And you'll see why that's important later on when I start comparing the beads to ones from elsewhere. So just to demonstrate why beads were so important and why they're found everywhere, this is an account from William Davenport's company in Liverpool, which is 20 years after the Rooswijk was lost. And he's talking about 250 bunches of beads, which is a tiny proportion of the cargo for his voyage. But he says, if I can't get hold of these particular colours, we may as well not bother going. So relative to the other goods being exported from London at that time, which is things like gunpowder, brass, cloth, iron, alcohol, these tiny glass beads are right up there in terms of their value. And they were transported by, they were threaded by colour, and packed in beads or barrels. So there's a lovely example, La Belle from 1686, where the preservation was very good, and they had over 800,000 beads that they recovered, and they were still laid in rows on top of hay in a box. Now in Rooswijk, the site is very mobile. The beads have been lost to the sands, apart from the ones in the concretions, but we do find them in particular areas of the wreck. So they're in the stern end of the cargo hold, and they tend to be in concretions with other trinket type objects like the copper alloy rings and the brass beads. So that tells us something about how they were transported. Now, we characterize them based on the type of glass, the type of colorants, type of opacifier, and also the structure, sort of how they were made. And a key point is that there's a transition in the 17th century from tin-based to antimony-based opacifiers. There are also different types of glasses used depending on the region that beads are made. So Indo-Pacific, Africa, Europe, you can pick up differences. So with sufficient data from sufficient different places, we can start to build a picture of where they were coming from, where they were going to, and what date they were made. I've got one eye on the time, so I'm going to go quite fast. The white beads are quite unusual. They have a cord structure that they're, despite being 3 millimeters across, this one, it's made of 3 layers of glass, 2 white layers you can see in the middle with the white calcium antimonate opacifier, and 1 colorless layer on the top. Now this is a type of glass which is a Venetian style, which was copied by the Dutch and then spread to England. So it's very difficult to tell apart this particular type of plant ash glass if it's made in the Netherlands or if it's made in England. It looks very much the same, so it could be either. Now the other beads were lead glass, and this is quite unusual, and it's a high lead glass. It's 70% lead, and this is why they show up in the X-rays. If you remember Angela showing the X-rays with the white specks on, this is the lead glass beads. Lead glass began to be used for imitation gems. There are some documentary references for it being used in Italy for beads in the early 17th century. So it looks like it's spread again because there's some archaeological evidence of lead glass beads being made in the Netherlands in the 17th century, but they're not very common. So I started looking for comparable beads from different parts of the world. There are some in Paris and Amsterdam, but not many. And then more interestingly, there are similar cord white beads found in New York State from the 17th century, and there was a Dutch contact there. And then there are similar yellow, green and white beads from Niger, again thought to be the 18th century, and that's where this photograph is taken from. So you can see those tiny yellow beads 3 rows down, cord white beads on the top row and the green beads on the bottom row. They're very nondescript. They're small and they're plain. There's nothing distinctive about them. And if we don't analyze them, we can't tell these apart from the same color and style beads, but made at an earlier date or a later date. So the analysis here is really key. The final example is the Amina Castle wreck, which is off the coast of Ghana. And this is thought now to be the wreck, again, of a Dutch ship. So you can see there's a theme here of the Groningen, and that was 1647. And again, you can see the picture of the beads given here. Now, they didn't do analysis at this wreck, but they did pick up that some of the white beads are cord, and they mentioned that they can see other beads on their X-rays, so they're highly likely to be lead. And this also gives conservators a nice cheap way of IDing these beads in their concretions because of the visibility of them. So you can see from the spread of the beads, these different find points, it's not really connected to the activity of the East India men like Rooswijk, which were going in the other direction. They're more to do with the activity of the West India men. And you can see from the location of the finds why these beads are strongly associated with the transatlantic slave trade. So very quickly, just to demonstrate the potential for archaeology, coincidentally, we were asked about another wreck. This is off the island of Guernsey, which is one of the Channel Islands. And the wreck is unidentified, so it's thought to be an 18th, 19th century Dutch vessel. And we were asked about it because there are hundreds of thousands of beads there, not in concretions, just on the sea floor. So we analysed them, and the lead glass beads match the ones from the Rooswijk perfectly. So it does confirm that this vessel is likely to be, again, connected to Dutch trade. Some of the other beads, though, are a mixture of lead and the plant ash glass, and they include the earlier opacifier tin oxide. So it looks that this ship was lost during that transition period. So just as the lead glass beads were being introduced, but while this transition between tin and antimony opacifiers was still taking place. So that allows us to suggest the bead wreck date be revised to the second half of the 17th century. And that may change the approach to managing this wreck site, because we've been able to suggest an earlier date. So I hope that gives an overview of the potential of this sort of analysis in archaeological materials, archaeological collections. Here, because we've been able to analyse material from a wreck of a known date, it sort of helps us establish our glass composition chronology. So it's extremely useful for other sites, especially because these European beads are all over the place on wrecks and archaeological sites all over the world. But this sort of approach can be used to refine typologies for any type of object, especially plain or long-lived styles where you otherwise have very little to go on. And it helps us also to look at provenance so that we can better understand travel and trade. So I'm going to stop there, hopefully, if I can work the technology, and hand over to Francesca Gradi, my colleague, who is going to talk about the coins from Rooswijk. Right, I just have to work out how to do it. There we go.
Good, thank you. I can't share my screen yet.
You will be able to do it.
Right, yes. All right. Can you see my screen okay?
It's okay, you can move on.
Perfect. So I'm Francesca Gherardi, and I work with Sarah at the Material Science Lab at Historic England. And today I will talk about the analysis of the silver coins from the Rooswijk. So it's quite important to understand how silver was moving all around the world at that time, to understand why we find so much silver coins and ingots in these shipwrecks. So first of all, after the discovery of the America, a lot of silver was extracted there and then was brought to Europe. And then from Europe, it was traded in Asia. So Europeans were able to sell and silver and buy gold at lower price so that they could resell it in Europe for double the price and make a lot of profit. And at the same time, also there were some Asian countries like China that they required a huge amount of silver. So this is the reason why a lot of silver was moved to the east. So before the discovery of the Americas, the majority of silver was extracted in Germany, in Saxony and Bohemia. There were also some extraction sites in Hungary, Sweden, Norway, Great Britain. But after the discovery of the Americas, the majority of the silver was coming from those sites because it was easier to extract and it was more efficient, and large quantities of silver could have been produced there. So here you have an idea about how silver was traveling. For example, from Mexico, it was traveling all around the ocean and arriving in Spain. And then from Spain, it was distributed all over Europe and then all over other countries in the East, in Asia. So Spain was a central and focus point, and this is the reason why also some Spanish coins were trusted currency also in other countries, because they were pure and they are like a standard weight, and this is why they were still used in other countries. So why are we interested to study the provenance of silver? So this is, we can do that because of this principle. So a unique mineralizing event is able to create an ore with a unique elemental composition. So if we analyze the trace elements of silver artifacts, then we can link them to the ore of origin. However, there are some considerations to make. For example, ores sometimes can be not very homogeneous in chemical composition. Quite often, silver extraction and then this subsequent refining techniques can make and change the trace element pattern. In the specific case for the coins that we're using now, sometimes the silver was coming from the Americas and then it was refined, so some other additives like lead, they were introduced, and these were from Europe. So you will see that you have like trace elements that were quite from basically two different areas. So as I said, metal recycling can sometimes make some unclear and indistinctive trace element fingerprints. And in addition to these coins were recovered from a marine environment, and and the corrosion that is happening there can also alter the elemental composition of the coins. However, there are several studies that demonstrate that gold and bismuth are important elements to consider while in a trace elements analysis, because they don't change during the metallurgic process. So we can track these two elements to find out where the silver is coming from. Obviously, so this presentation will focus just on trace elements analysis. However, it's important to underline that the best way to characterize the provenance is also to combine trace elements analysis with also silver, copper, and lead isotopes. In particular, in silver coins from the same time as these ones, other researchers study not only lead isotopes, but also silver and copper isotopes, because again, as I said before, a lot of silver was coming from the Americas and it was mixed and remelted in Europe. So other additives were added from European sources. It's, as I said before, it's quite important to evaluate the silver extraction and refining techniques. Since ancient times, smelting and cupellation was the most used one. With smelting, basically a metal ore was heated up with a reducting agent like charcoal, and this was able to extract silver from argentiferous lead ores like galena, for example. And then the cupellation was another refining method to extract silver. So this way was very spread, and it was the main one used in Europe. However, it required a huge amount of timber, which was not really available in the Americas. And so this is the reason why the patio process came into place. The patio process was introduced was developed in Europe, but introduced in the 16th century in Mexico. In this case, the ores are crushed with salted water, and then they were mixed with mercury. Copper sulfate was also introduced, and then in this case, the amalgam was formed, and then silver was extracted by heating it up and after the evaporation of mercury. I'm mentioning this because, as you will see from the data that I will show afterwards, we can still see like traces of mercury in the coins that were produced where the silver was extracted using this process. So the coins from the Rooswijk are of two categories. So we have Dutch coins, Dutch that were minted in Europe. They were Silver Rider, Ducaton, and Sixtover. And then on the other side, we have the so-called Spanish coins, the Pillar Dollar, 8 Reales, Cob 4, and Cob 8. as I said before, the Spanish coins, they were spread all over Europe because they were a trusted currency. Here you have an idea about the time frame, how they were spread. So the oldest coin is from the 16th.
Francesca, you have 5 minutes left. Huh?
Okay. So the oldest is from the 1618, and the newest is from 1739. And so the Dutch were basically minted in Europe, as I said before, and also while the Cob 4, Cob 8, and the Pilar Dollar, they were minted in Mexico and in Bolivia. Here you have an idea about the location of the mint in Europe and in the Americas, in Bolivia and Mexico. So why are we using the analysis of coins? So we want to study the purity of silver. We want to find out about the provenance, to find out about the silver extraction procedure and recycling. The majority of the coins were composed of silver, over 95%, and then with 3–4% of copper. And then what we are more interested to were the trace elements that you see here, in particular lead, gold, mercury, zinc, bismuth, nickel, and iron. We use micro X-ray fluorescence spectroscopy to analyze in a non-destructive way the coins. This allowed us to analyze the coins directly without taking any samples. As I said before, the coins had a corrosion patina on top. So under the microscope, a small, tiny spot was scratched on the surface in order to access the bare metal and analyze the bulk of the coin. Here you have an idea about how the composition of the coins. As you see, the concentration of silver and copper was quite comparable in different coins, except for this coin, a shelling. And then, as you see here, the concentration of the trace elements were quite different. So as you can imagine, we had a huge amount of variables and a huge amount of data. So we tried to find a way to represent all of these data in a simple way. So we applied principal component analysis. And in this case, principal component analysis is a statistical method which is able to summarize and simplify the different variables, which in this case are the different elements, in two main variables. In this case, principal component 1 and principal component 2, as you see here. This is how the different variables are distributed in the graph. So for instance, coins that are in this part of the graph are richer in gold, and coins with this part of the graph are richer in bismuth. And this way we're possible to represent about 70% of all our data set. So as you see here, we have three main groups. So from one side, we have all the coins that we know they were minted in Mexico and they were with Mexican silver. Then we have a coin minted in Bolivia and from Bolivian silver. Then we have these coins that we know that they were, according to the literature, these were rich in bismuth, and this indicates that the silver used was coming from Germany. And the rest of these coins, they were minted in Europe, but by using mixed ore, so mixed silver, either from Mexico, Bolivia, and Germany as well. So you can see the difference between the silver used in the Americas from silver coming from Germany, because the amount of mercury was higher. This indicates the silver in this case was extracted using the patio method that I mentioned before. If we can just focus on the Spanish coins, as you see here, it was clearly possible to discriminate between Mexican coins and Bolivian coins. So this helped us to visualize the different coins coming from the Americas. And then here you see the results of different coins that were minted in Europe, which is quite, you see the different colors represent coins that were minted in the same location in the Dutch Republic. And we have an interesting data set here. These were just coins that were minted in Overijssel, which was one of the provinces of the Dutch Republic. And in this case, the coins have a specific pattern, which is indicative of silver coming from Germany. So in this case, historically, we found out that in that year, in that specific Dutch Republic, there was that specific province was more independent, and so probably the relationship with the trade relationship with Germany were preferred. So this is the reason why they were using just silver coming from Germany rather than the earlier coins that were using mixed silver coming from the Americas. This is the conclusion and the summary of the data that I've just presented. And here you have some contacts and further resources. If you're interested in this project, you have the website where you will find some blogs about different artifacts recovered from the Rooswijk. Then if you want, you can also join the virtual dive trail and also look at some 3D models of the artifacts, and obviously following on different social media. So I also would like to thank the organizer for inviting us to speak, and all of you for listening to us.
Thank you to all the speakers of this fantastic presentation. Thank